Hello everyone. Today I'm going to show you how to check or verify the energy balance for a heat transfer simulation carried out in SimLab using a AcuSolve solver. Here is the model description. A simplified underhood model is being considered for the simulation where engine and few other solid parts are included. Boundary conditions for the simulations are air is entering through the inlet phase with a speed of 50 km per hour at a temperature of 45 degrees Celsius, and outlet is being kept at zero static pressure. And other boundary conditions are like engine is considered to be like at a constant temperature of 400 degrees Celsius, and few parts like board, control panel, clip or the plastic parts are kept at a are applied as a zero heat flux condition. So let us jump into the SimLab and import the model, and then set up the meshing parts, and then go for the further simulation setup. So I'll jump into file, import, solver input file. I have a surface mesh ready, so I'll directly import, start with the surface meshing. So I have selected the Nastran file. I'll keep the default as it is and just click on the import. Now let us understand the model. So we have a domain around it, say internal, and that is called fluid here, and there is the fluid one called as an engine block, and then we have the clip, control panel, and the board. Okay, these are the few parts which are there in the simulation. So now to make as I'm considering engine to be a constant temperature, I don't want the 3D mesh to be generated inside the engine, so I'll make it as a bluff body, or just like to apply the constant temperature condition. So for that what we have to do is we have to merge these two surfaces. So I'll change these to surface and say show you. So I have to merge these two bodies so that there will be no mesh generates inside the engine block. So for that I have to click first the fluid and then fluid one, then right click and say merge. So whichever you have clicked the first time, that will be retained and it will be merged. If I just show you that these surfaces are right now merged into a single body. Okay, and then we have other parts as three solid bodies. So what I will do now, as I have to create a mesh for these bodies, as these materials these are made out of plastic parts like HDPE material. So what I will do, I'll create a face out of this, like I'll make a shared face from this. So I'll do this from geometry, create from faces, select these surfaces, and there's an option, select an option, duplicate and make shared faces, and say apply. You see there's one more part is created with the name as a clip one, and just say cancel. Now we have this part present and rest of the solid bodies as well. So now again what I will do, I'll skip from here, hide these solid bodies, keep these two right now, and again we need to merge here. Okay, so right now if I merge this, all will become into a single green color part. I'll select the fluid first and clip later, and then click on the merge. Okay, now if you look into this one, everything is showing as a green color. Now it means the whatever the outside domain is completely air, and what is left inside is a hollow. So, and also I'm keeping these as a separate, so that I want to create a 3D mesh inside this as well. Okay, so now our model is ready for the volume mesh. So I'll take a section cut here to see how this looks, right? So this represents air and these are some solid parts. So I could see the section cut filled out here. Okay, close the section cut, and then okay, now next, as I have already a surface mesh created model, so let us jump into a volume meshing. So let us go to the mesh first, and then I'll go to the CFD mesh, then choose the body of a fluid bodies, select this body. Either you can directly select from this interface, or you can select from the assembly browser here. Okay, and then which faces of the, which are the faces where you want to, you don't want to generate the boundary layer. It is the inlet and the outlet. Here I don't want to see the boundary layer is normal to this face, but I want to see the inflation layer on these edges. And then what are the solid bodies? Select the solid bodies. As these are not visible from here, you can select from clip from this assembly browser. So these three solid bodies are right now selected. Now how do you want to generate the boundary layer parameters? The first layer thickness definition based on these two options. One is constant, other one is the fraction of surface mesh. So constant is that you have to determine the size and you have to specify it. For the fraction of surface mesh, so I'll be saying as a factor of 0.1. So if you have the varying surface mesh on a boundary on a surface, you can use this as a factor and it will generate 0.1 factor of that surface mesh. Say suppose if your surface mesh is 1 mm, your 0.1 factor of that 1 mm will be a 0.1 mm. So I'll be choosing in a factor wise. Then I'll use the total number of layers to be 6, and growth rate I'll keep it as a 1.2. Then it'll ask me whether what kind of average element you want to create. So generally I would be creating like as of the surface mesh of this wind tunnel, so that is right now a 10 mm mesh, so 0.01 meter, or I can change this unit system anytime, and I can work with the mm unit as well. So 10 mm, then internal grading like growth rate I'll keep it as a 1.2. Now the meshing is started. You can see at the bottom that it started the meshing. So let us wait for a few minutes. Okay, now the mesh is completed. Earlier all these wireframe bodies are turned into a solid bodies. Now we can see that all these are meshed out. I could right click and check the details about it, so that I can see the total number of nodes, total number of elements. Also I can take a section cut, slice plane. I could see the mesh on the three bodies and the fluid domain. And okay, and then once the meshing is complete, we can assign the material properties to these components. Like we can directly click and change the material properties and assign the proper material. So all these solid bodies are assigned with HDPE and fluid is modeled with the air. Okay, and then now let us go to the solution browser. There's nothing in the solution browser. Now go to the menu bar, solution at the top, and then pick the physics flow, and then you see a pop-up. Okay, in the pop-up it says which is the solver. Flow solver right now, solver is AcuSolve, solution type is steady or transient. Right now I'll use steady. And then for the bodies, I'll select all these bodies, so that I am saying to the solver that these are the parts, solid parts to be involved. And then physics, I am selecting incompressible. The flow is turbulent and it is modeled with the Spala-Talmaras one equation turbulence model, and also heat transfer is enabled, and even the radiation is considered through the enclosure modeling. And then say okay. Once you say okay for it, then we see that solution browser appeared and few of the things are already set up. So right click on the setting now and go for a solver settings. In the solver settings, I'll use most of things default. Only I'll change the how many number of time step I will want to use, and what is the convergence tolerance for the all the variables scalars to be solved. And then I'll use the relaxation factor of 0.5, and that is it. So rest of the parameters I'll use as it is. You don't need to change all these advanced parameters. And then say okay, and again it's taking time. Again right click on the settings and go for the format and execute options. Here I will be selecting the number of processes, And also most important thing is I'm disabling the auto wall, so that all these surfaces are separated based on the volume regions. Okay, and then say okay for it, and let's keep everything as a default. Okay, now we need to set up the boundary conditions. Let us start with the ribbon bar. Let us go to the first initial condition, and initial condition type temperature I am selecting. Select all the bodies, and the temperature I'll say 45 Celsius is my ambient temperature. Okay, and we can directly write 45 and see, so that it will convert into Kelvin, and then say apply. So you can use velocity, pressure and eddy viscosity if required, then say cancel. And then there is no heat source involved, there are no fans in this simulation. Let us next go into the inlet condition. So in the inlet boundary condition type, I'll select the phase, and then the inflow type I'll select velocity or average velocity, or the based on your equation. Here I'll select the velocity, and it is velocity type is normal to this phase, and velocity 50 km/h turns to be 13.88 meters per second, and temperature is 45 Celsius. And most important thing is, for all the surfaces we are going to request the nodal output frequency, so that it writes out heat flux information in the in the solution, and say okay. So once inlet is defined, I'm going into outlet and pick the other phase and keep the everything as a default, and say apply. Okay, and then cancel. Now I'm going to define these all the four surfaces as a slip condition. I don't want to involve these into simulation. So when it's very small, I could directly make it as a slip condition. And again, don't forget to request the nodal output frequency. Now we have seen this, right click and say hide the entities. Now we have left with the inner bodies. Here I am going to select the wall condition and pick the engine wall and assign it thermal temperature, like condition type, to be temperature, and again make it as a 400 Celsius. It will convert again into Kelvin. Then select the nodal output frequency to be 1 and say apply. So you can rename it accordingly, so with the proper names here. And then we have these three bodies left out. So first I'll use this, again no slip condition, and select this surface and give a name as a board. And then this is not again a temperature, constant temperature type. I'll use the applied flux, so that I'm not going to assign any boundary condition on it. Then again do not select this one and say okay. And then similarly I'll select for these two bodies. Okay, again select this board, applied flux, say okay. Okay, select this other control panel and say apply. Say yes, it will. So as some of the surfaces are common to two of the solid, it says that you already selected few surfaces out of it. Say cancel. So we are selected few components and the flow boundaries are defined right now. So I'll rename it with the proper name, like this surface to be engine wall, and then rest of things again are defined as a board, clip and control panel. Okay, so now we have defined the temperature, like thermal related boundary condition. We need to define the radiation related boundary condition now. So let us switch on the full model go for radiation parameters. I'm going to use the default as I'm using the enclosure radiation modeling here, so I don't need to change these symmetric planes. Say OK. Next important thing is to create the radiation surface. So here emissivity model, so radiation surfaces it requires. So I'll select all these parts, including all the parts. I'll select this, and these are like involved in the radiation heat exchange or heat radiation simulation. And then I'm going to define a emissivity model here. So emissivity, I'll say that emissivity of a 0.95 I'm going to consider with some yellow paint. Okay, emissivity, then say OK. Emissivity is defined right now, and then these surfaces are assigned with this emissivity, and then say apply. And there will be two more surfaces I need to define as a openings. When I turn into opening, other inflow and outflows are right now visible, so I could select these surfaces and say what is my opening temperature, like again ambient temperature. Okay, and then say apply, and then we are done with the boundary conditions here. Okay, we could see the radiation related parameters, boundary related parameters. Then we have already requested the solver settings. Okay, so I think right now we can directly right click and say click on the update. So if I click on the update, it will try to solve in this local system here by using 8 cores. Okay, then right click, say update. So let us wait for a few minutes again. Now the result is completed. We could see this green color check mark here, and on the results. Now right click on the result, and we can look for the view solver log file, and we can monitor, we can check the log file for conversions and for other information. Okay, and the simulation stopped at the end of 45 time step, as this all the variables like radiation, temperature, viscosity, pressure and velocity are all well below 1 e raised to -4 what we have requested as the convergence tolerance. Okay, right click and then look into the plot convergence, and once you click on that, you will see another pop-up, and AcuPro will be launched. Okay, so in the AcuPro we can see all the 2D plots for all the surfaces. Now first I'll check the residual ratios, how the convergence looks like. Okay, all these parameters are nicely converged to 1 e raised to -3 and -4, and also the radiation outputs are requested for surfaces. And for the elemental, so we have 4 element regions here, 3 solid bodies and 1 fluid body. For those we have all the outputs written for the deck. And for the surface output, as we have only like 3 bodies here, right, 3 surfaces present. But if you look at into this surface output panel, you see more surfaces are showing here. That is because we have disabled the auto wall, and the solver distinguish the surface between 2 regions, which surface belongs to which volume. So if there is a say for example, if you consider this surface control panel, it is one side is attached to a fluid, other side it is attached to a control panel. That's how it distinguishes. Okay, let us jump into results right now, and as the result is loaded, I can directly display result, and I can see the temperature. First I'll take a slice plane, okay, and then remove this. Okay, so If you refresh it or reset the range, so temperature is okay. Just a minute, why it is not updated? Yeah, if you look at this, 400 is the highest and 45 is the lowest, as most of this region is in the blue color, so it's like maximum is almost 100. So let us adjust this to 100 degrees Celsius, and we can see the temperature contour. As the air is blowing from this side, we can see this, the temperature heat is dissipated through the air. And then change this to velocity variable scalar, and then we can see the velocity distribution in this at the center of the panel. Okay, so we are very much interested on the heat balance and the energy, or like what are the each phases, heat flux on each phases, and how it summed up to make the complete energy balance. To find out that, we need to uh, use a AcuHeat balance script that we can access from the uh, command prompt. So I'll open a command prompt, and I'll go to the navigate to the working directory here, and have the log file and the result file present here. I'll run the script called AcuHeat balance. AcuHeat balance -h gives the uh, options and usage for the AcuHeat balance script. Like, it will give you the arguments and the explanation about it. So I'll use the AcuHeat balance -pb is the problem name, that is the same problem name, and then flow is the name of the INP file, and then I'll enter it. Once I enter it, it prints the information about the element set, surface sets in the console, and also it writes a file called its text file in the working directory, that is individual balance and a total balance. AcuHeat balance is a post-processing utility that uses the AcuSolve database to compute the energy balance within the solution, and it is most of the times mostly used for a steady state solution for the Navier-Stokes equation. Wherever there is a wall boundary condition is applied, the surface integrated heat flux is calculated, is summed up to provide a total heat loss or conduction and radiation. And similarly for convection, we have to sum up all the convective temperature flux to find the total heat loss gain due to convection. That's the main important thing here to understand. And then already spoke about this, how this script we have to use, what is the significance of these files written in the console, and this is the formula being used to calculate the percentage balance, where QI stands for heat flux, and then NW for wall surfaces, N inlets, and N outlets for the inlet and outlet surfaces. And these are the two files written in the working directory. We can take this, it's a comma separated file, we can take this to Excel sheet and then arrange in a proper element set wise and the column wise, and then have done this for complete solid and fluid involved to find out the convective temperature flux and the heat flux. If you take the summation of all this, it is close to it's the total on both sides is almost equal, and the difference is only a 0.14 watts. That is almost like 0.01%. So, and as this simulation involves radiation as well, we can see the radiation balance is as well 0, 53.65 watts and minus 53.65 watts. This is for the total heat balance considering all the elements set. And if you do the same thing based on the element side only, for on the fluid side only, on the solid side, you could see that still it is almost like the difference between the heat flux and convective temperature flux is almost 0.09 watts. It's again close to 0. And with respect to only on the fluid side, it is again almost like 0 watts. Some of the best practices is that we should not be missing any of the interface or boundaries for the energy balance calculation. If you miss it out, there will be a differences it shows up. And also there should be a mesh sensitivity study should be conducted at the beginning of the solution. And in the past, that with the y plus of targeting less than 5 gives a lesser energy deviation, lesser energy imbalance. And also negative heat flux means for a radiation is absorbed by the solid. And to sum up everything, so our goal is to set up a sample model to understand how the energy balancing works with the IQ heat balance utility. And first we started with the importing a surface mesh and volume meshing, and then set up the physics, set up the whole simulation parameters, and most importantly set up the model frequency for uh, each surface output, and then run the script and segregate the data using an Excel sheet or some other tools, and then finally perform the energy balance for fluid side and solid side separately to get the complete energy balance within the heat transfer simulation.